Okay, everybody, welcome to another Monday. It's our last official Monday of classes, actually. Next week we have our final exam. Final exam will happen at 11 o'clock on Monday. Let's take a look at the schedule real quick here. It's going to happen at 11 o'clock in the morning on the 19th, which is next week. If you don't like the 19th, you can come on the 21st. I still don't have the date for you yet, but I'll have the date probably within the next day or so. Actually, I might even have it by the afternoon. We'll see what happens. I want to say 11. I want to try to do it the same time period at 11. 11 to 2 or 11 to 12, 11, 12, 1, 11 to 2-ish. So we can tentatively plan for 11 a.m. on Wednesday. How's that sound? So come at 11 a.m. on Wednesday if you don't want to come at 11 a.m. on Monday. But I'm only going to have one time slot on Wednesday, just from 11 to 2. But if you don't get in the door by noon, you can't take the test. So come at 11 if you're going to come on Wednesday. So, all right, so now that that's taken care of, let me go over what's on the exam. I rewrote the exam because I looked at it, and then I looked at the questions, and I looked at the answers, and I looked at everything, and I went, oh, this is way too hard. I originally put together a multiple choice exam for you. And the multiple choice exam, I gave it to actually a student, and they failed it. So I decided multiple choice is too hard for this course. It's actually a hard exam. So I figured it might be easier for you to have short answer, because at least you could write something that you know about it. Believe it or not, it's easier to get a better grade on a short answer exam than it is on that multiple choice test. Because the multiple choice test, you have to know the answer to get it right. This one, you don't have to know the answer. As an example, let me go through the subject areas. It covers the entire course. That's 9 or 10 chapters, actually, if you count up the chapters. It's about 9 chapters worth of material. So if I asked you a very specific question about, as an example, system call interface, you may not be able to answer that question, but you probably could remember what the system call interface was. So if you're making notes to yourself, and I'm recording this so you can actually just read this, listen to this again if you'd like. I'm going to go through question by question. The exam is worth 25 points. So there's 30 questions, which means you can miss 5 and still get an A on it. I have 5 bonus questions. So if you answer all 30 questions, you're in good shape. Actually, let me count. Let me just see one quick real. I have 15. Oh, wait a minute. Wait a minute. I took the 5 questions off. I lied. I lied already. There are 25 questions. There are 15 and 10. Yeah, there are 25 questions. I'm sorry, I lied. No 30 questions, just 25 questions. I took them off because I thought the exam was too long. So I did this last week, and I had to refresh my memory on it. But I'm sorry. There's only 25 questions because the exam's longer. Because you have to write the answers instead of actually answering multiple choice. So you don't want 30 questions, you want 25. However, I put the easiest questions I could possibly put on here. So it's pretty easy. So it's short answer, which means it's a couple of sentences or so. Harder to cheat on this exam as well. Because on a multiple choice test, and let me tell you, we just finished the weekend, and you can see people looking at other people's papers, and because the seats are so close together, it's very easy to cheat on this multiple choice kind of format. So to make your life better, we don't have to watch you as much. No two people are going to write the same words in the same order in the same exact way or express their ideas identically the same. So it's a lot easier for you to put your own original work on there and not have anybody cheat from you. Especially it's also hard to read writing from a distance. It's easier to see something circled. So anyway, long story short, no notes, no internet, no sharing of, no talking to each other. It's a individual exam that will occur. 25 questions of short answer. Short answer is 1 or 2 sentences. It's not like a lot of writing. If you run out of space, there's going to be extra space on the back of the sheets that you can write on. All right, question number 1 is on the concept of the system call interface. Know the system call interface, which is chapter 1 of the book, actually. Regardless of which version of the book, it's always chapter 1. So the system call interface deals with the concepts of dual mode operating systems, where we have a kernel mode and a user mode. And you know that from the user mode, the user creates system calls that goes down to the kernel mode, asks the kernel something to do, and in that sake, the kernel wakes up, does something, performs something for the user, and then we have these concepts of interrupts that occur from hardware. So the hardware interrupt sends signals up to the operating system catches them, and they from an OS level, the kernel catches those interrupts and processes them, puts them up in an interrupt table, and runs whatever, send the user mode a message that says the CD-ROM drive is open, or that it just closed, or for status and stuff like that. And so the system call interface, and the purpose of system calls is for the user to communicate with the kernel. From a hardware perspective, the user doesn't communicate with the hardware. It communicates with the kernel. Kernel communicates with the hardware through the interrupt calls and signals. So the kernel can also send a signal. The signal, sort of think of it like a flare up to the user mode, and the user mode says, hey, the CD-ROM drive just shut, or something, it's to communicate with the hardware, vice versa. So the concept of the dual mode, the kernel mode, the user mode operation. So the first question is getting at those concepts. So if you're familiar with those concepts, then you'll have a good chance of being able to answer the question. There's many different ways that you can answer that question. There's not just one right answer, which gives you the benefit, because if you're familiar with system call interface, then you can answer the question and you'll have a good time with that. All right, so question, we have any questions? In fact, this is your opportunity now to ask questions about system call interface or system calls. You guys did this with your first assignment. If you've done the first assignment, you wrote a shell, and the shell worked with system call interfaces. All right, so question number 2 is signals, semaphores, and interrupts and system calls are included in that. Signal. Okay. Purpose of interrupts. And what do we use interrupts for? Is question number 2. And do we know what a trap is, actually? Software level interrupt, but it's more than that. It's one that's not created. It's an interrupt that's not created by the hardware. It's usually created by software. So when you say software level interrupt, if you were defining example, let me give you an example answer here. If you were defining it, if I asked you, it's not on the exam, but if I say, what's a trap? And then you come back and say, if you said, well, it's a software level interrupt, I'm going to be like, all right, but can you say a little bit more than that? So if you can say 2 sentences on that, say it's a software level interrupt, it's generated by the user mode or the kernel mode, but not the hardware. Then I'd understand what you're talking about as an example. So you don't have to write a lot, just write more than, it's bad, it's good, it's fast, it's slow. Don't use those words for anything. Nothing is ever bad, nothing is ever good, never ever fast, or nothing is ever slow. Why do you want to use a trap? It's fast. No, that's the wrong answer. Questions about traps, interrupts, signals, system call interface. Again, it's really chapter 1 of the book. It's getting into that. Nope. Then let's move on to chapter 2. What is chapter 2 on? Resources. Services. Operating system services. Let's take a look here. So there's about 2 questions from chapter 1 on system call interface, interrupts, stuff like that. There's 1 question on operating system services, and I'm reading operating system services right there in the question. So there's only 1 question on the exam on chapter 2, operating system services. Not such a big deal, really. Kind of a small thing. But chapters 3 and 4 were on threads and processes. There's a lot more on that. So, let's see. Where do I begin? You know the difference between a thread and a process. You know what a process is. You know what a process control block is. So let me review a little bit about the thread and the process concept. They're abstractions. If you think about it, isn't a thread and a process the same thing? One of them is from a user mode perspective. The other one's from a kernel mode perspective. Yeah. And don't they, and you could also argue and say, well, no, that's the same thing because a thread lives inside of a process. And you'd be right with that as well because we have mapping. some older operating systems, there was a lot of experimentation with mapping where we took one process and mapped it to 5 threads. And we say, well, where's this mapping occurring? At the kernel mode. So it's one user level process mapped to 5 kernel level threads or something. So we have a little mapping idea. There are no mapping questions, however, on the exam. You don't have to know about thread mapping. You can say that a thread is it's kind of a lighter weight process in some ways. If you described what that meant, that'd be a correct answer if I asked you what the difference between a thread and a process was. Because a thread is generally spawned or created, forked from a process. And so it lives inside of the process space. So is it really lighter weight? No, because it actually gets a copy of everything that the parent process has. And it takes up the entire parent process space. But only one thread runs at a time. So, and you figured that out if you did some of the assignments in the beginning of the course with the threads. So long story short, you'd have to elaborate a little bit. So come up with a good idea about what a thread is. Come up with a good idea about what a process is at a basic minimum. And then a process control block is where the threads live. Well, they don't really live there. They live in memory. But the kernel keeps track of all the threads in the process control block. So the process control block is a data structure, actually. It sits in the kernel level, and or resides in the kernel level, I should say. And then it holds all the information about each process. Where it's located in memory, what is it received in terms of CPU time and I/O time, and how much processing has been done on it. Basically, long story short, it's managing the life cycle as well, and not the life cycle, but the running of the particular process. Threads have a life cycle to them, and they get started, and then they're ready, and they're paused, and then they're running. So they have different threads, and processes have different cycle phases that they go through from the beginning, at the time that they're created until they're terminated. So think about the life cycles as well, and that's how the thread's being controlled by the kernel, because not all threads, only one thread or one process is running at any one moment of time. We know that from CPU scheduling. So the thread format, the thread architecture, is strongly mapped towards its use with CPU scheduling, because the CPU scheduler is the one that's going to be able to essentially manage and orchestrate the threads. If we go into the class here, I've been sitting at this menu. This is really just an audio recording versus a video recording for the most part. But all of the lectures in here, I was going to open it up here. If you go into the bhacker.com or go into the EMS, they're in there as well. You can review all of the recorded lectures, but you may also want to take a look at the PowerPoint lectures. They're just a snapshot. I believe we've gone through 9B, which is where we're going to finish today. So 10, 11, and 12, 10, 11, 12, and 13 are not on the exam, by the way. So if you don't have a copy of the book, and the book is all over the place, so hopefully you do have a copy. That's the best resource to study for this stuff. Outside of that, you can look at the lectures in here. It's going to give you a snapshot of the information. And the information on the exam comes out of the book, by the way. The questions are similar. Every one of these questions can be answered with the reading material from the book. So if you have the time, I highly recommend reading the book, actually. I wouldn't focus too much on Chapter 2. It's kind of a lightweight chapter. But Chapter 1 is important, and Chapters 3 and 4, 5, CPU scheduling is important as well. So the heart of the exam is in the first part of that, and then also memory. So, okay, so getting back to the concept of the process and the thread. Also the concept of interprocess communication, IPC. Because what do we do with the assignments? And the exam is basically based off of the assignments. We had what? We had students going to office hours, and we had to orchestrate their behaviors. We had a copying a file using a consumer-producer model. So be familiar with the different models: readers, writers, producers, consumers, dining philosophers, and what interprocess communication is. And then we come up with that word you mentioned earlier, semaphores. Mutexes and semaphores. So it's the operating system kernel level support for interprocess communication. That's what a semaphore is being used for. And semaphores, well, if I can probably describe interprocess communication for you in a couple of words here, just to give you the big picture. It's direct or indirect. It's message passing or mailbox. It's however you want to remember it. Either you're going to have one process communicate with another process through a semaphore interface and say, hey, wake up, hey, sleep. And then I get told to wake up by another process. Okay, I can wake up. Now I run and I tell somebody else to wake up and I go to sleep. And when the processes themselves are directly communicating with each other and telling them what to do. Or there's a shared memory or mailbox approach where processes go to some central memory location and they check for a mutex. Is it on or off? It's like a light switch. Is the switch on or off? Is the door unlocked or locked? We're doing that because of the concept of mutual exclusion, and we're creating mutual exclusion through interprocess communication, having those processes cooperate with each other. So you want to know what mutual exclusion is as well. To keep some, and then also the word critical section or critical region. So mutual exclusion, by definition, takes and creates an environment in which only one process at a time can go into a critical region. And then people go, well, then what's a critical region? Well, a critical region is the area of the code that you're trying to protect. Inside the critical region or critical section, sometimes called section, sometimes called region, always called critical something. It's critical because if two processes were to be in there and we weren't upholding mutual exclusion, we'd probably have some data corruption. Or maybe we also have some lost memory. Or we have some processes that can't perform as they should be able to perform. So know the words a critical region and know mutual exclusion and those concepts and how they relate to interprocess communication. Be familiar with how processes communicate with each other and the different modes of interprocess communication, direct, indirect, mailbox, and the different ways of dealing with interprocess communication, the use of semaphores and mutexes, and the use of, well, Java uses monitors. You don't have to know how any particular operating system does anything. It's a very general, generic concept exam. I'm not going to ask you that, you know, what semaphore library does Java use? And you don't have to. If it was a multiple choice exam, I'd be going, what semaphore library does? And you have to go, monitors, semaphores. Oh no! It makes it much harder to answer that question. Here, if I said, how does an operating system handle interprocess communication? As a better question, you got more to answer with depending upon what you know. That's why I say you're going to like this type of an exam. It's much better than that multiple choice one. Nobody passes the multiple choice one. No, I gave it to a sample student already. They failed it. They didn't even get 50% on it. Because you only have one question. You have 4 answers. And, you know, yeah, okay, it's easier to take that exam because if you just don't want to take it, you're just going to blow it off. You just go, boing, 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 boing. You know, it's easier to mark the questions off. It's also easier to cheat because you can look over and go, what is that? Oh, looks like they got number 3 marked. Okay. And you can mark number 3, you know, you can match somebody else. Oh, somebody else thought that was good. Okay. You know. But long story short, it's impossible to get them right. Unless you know what a monitor is or a semaphore actually is. So this way it's easier to fake your knowledge, actually. When you can just say something that you're familiar with, because you might tap on it, you might get partial credit for it as well. With a multiple choice question, it's either true or false. I mean, it's either a point or it's a no point. But here you get partial points. You know, like, oh, they came close. So you can kind of like give them credit for it. Alright, so moving right along, we also have the concept of CPU scheduling, as you might imagine, Chapter 5. And as I mentioned, these chapter numbers, they might differ according to the version of text that you have. In the older version, I think it was 3 was processes, 4 was threads, 5 was CPU scheduling, or something of that nature. So, talking about the chapter on CPU scheduling. You want to know the differences and have a kind of familiarity with the concept of CPU scheduling. We know that CPU scheduling from a few minutes ago works with the process control block. Know the concept of context switching. What happens with a context switch? Well, you know, the CPU is running and the kernel decides, well, it's going to stop the running process, update the PCB, put the process to sleep or tell the process to wait, and then maybe if it has to pull the process out of memory to replace it with another process, depending on how much memory is available, Figure out, well, where did that process stop its processing last time it ran. Find out what next line of code is going to run for that process. Load it up, run that process. So know the concept of context switching. Context switching means you're switching between different processes, and you're updating the PCB, and you're allocating time to the process, so the processes can pretty much take advantage of the single CPU environment, but we have multiple processes running simultaneously, sort of. It gives you the illusion of that. So CPU schedulers determine the amount of multi-processing that's happening. Gives us the illusion. We have short-term, long-term, and medium-term schedulers as well. We don't want to put everything in one job queue. If we put everything in a job queue, everybody's got to wait behind everybody else. We know that the CPU runs simultaneously with other I/O devices. Hopefully, if we don't know that, know that. If you have everything in one queue, you don't break it out into short, medium, and long, or any other queue separation, then you have a I/O bound process waiting behind a CPU bound process. Not that big of a problem. CPU usually runs faster. So your I/O process, it's going to be slowed down a little bit, but let's reverse it around a little bit. Put the I/O process first and put the CPU one second. Then the CPU's got to wait for an entire CD-ROM to be read before it's going to get to run. Not such a good thing. So if we separate the processes out by where they're bound, which is what the short term does. If you answered and you told me short-term processes where processes live for a short amount of time, I'm going to say, you know what? You understood the question. Well, why? So short-term is CPU-bound processes. They also get a shorter quantum time. They may not actually be in there for a shorter amount of time. That's actually, my generic answer I gave you is technically wrong. Because sometimes the CPU's bound processes stay in that short term longer. Yeah, and sometimes they even get moved out into the medium term. What is the medium term? Well, it makes the short term smaller. It's a holding ground. This is a really time-consuming CPU-bound process. It's eating up too much time. Put it in medium. You put it in medium, then occasionally you go to the medium and you pull it out and you use it. It's not going to slow down everybody else in the short term. The short term is supposed to be a fast queue. It's a get them in, get them out as fast as possible. If you break it out, you can put a different scheduler on there. Short term is usually first come, first serve. Comes in, it goes out. Comes in, goes out. Comes in, goes out. Versus a medium term that you can put a round robin on. Oh, we got these long. Somebody put this mathematical calculation in here, and it's really taking up the coprocessor, but it needs to hit the CPU because they're bound together. Oh man, it's going to take up too much time. Move it into the medium term, and then all those little short term ones can run faster. And get those out, and then okay, we're done with the short or empty. Go to the medium. Now the medium's now a replacement for the short term. Long-term scheduler, long-term queue is I/O. Every process that's bound for I/O is in a long term. Sometimes they call them the job queue. So sometimes actually the word job queue actually gets used incorrectly a lot, actually. Some people call the short-term scheduler the job queue, when really the job queue is the long term. Everything goes to the long term first. We're going to run this job. Most jobs on modern day computers are using I/O. That's why we have these, fancy screens, and we have the keyboards, and we have all this stuff. Everybody's using I/O, so stick them in a long-term queue. Do they stay there a long amount of time? Not really. Doesn't really matter how long they stay there. They're not necessarily staying there any longer than in a CPU, than in a short term or a medium term. The length of how long they're staying doesn't really matter. It's where they're bound. Also, the preemptive behavior changes. In a short term and a medium term, they're preempted. We're going to cut it short. We add preemption in there to make it fair. Because everybody's in there, we're using a first come, first serve. Let's preempt it, if that's the case. You can preempt the CPU, no problem. In fact, that's the concept of CPU scheduling. We have to preempt the CPU. If we're I/O bound, we're not going to preempt. So most of those jobs in actually all the jobs in an I/O queue, the long-term scheduler, are not preempted. So they're non-preemptive jobs. Why is that? You're halfway in the middle of reading a CD-ROM drive, and you're going to cut the process short. What are you going to do with all that stuff? The cost of restoring the process the next time it's going to run, if you preempt it, is too much. It's longer than if you just don't run the process at all, or stop the process. Don't stop the process. Let it run. So to preempt means to stop the running of a process. Know those two words. I'm not going to ask you what is the definition of preemption, but you're going to be asked a non-preemptive job in a long-term scheduler, yada yada yada. What's the da? And you'd be like, well, I don't know what preemption means. So if you don't know what preemption means, you're not going to be able to answer the question, really. But preemption is to stop short. You're going to preempt jobs in a round robin. You may not preempt jobs in a first come, first serve, actually. So you may not use a first come. There's no guarantee the operating system is going to use a first come, first serve for anything, or a shortest job first for anything. Those are different algorithms, by the way. So we have shortest job first, first come, first serve, multi-level nested queues. Most operating systems are using a multi-leveled queue structure these days. You don't need to even know that. In fact, I don't even ask you about scheduling algorithms. So you don't need to know that either. But it's nice to have the knowledge, and then you know the preemption versus the non-preemption kind of behavior. If you're doing a round robin, you have to preempt that. How are you going to do a round robin without preemption? Then you've got a first come, first serve, or a shortest job first, or just a circle of jobs running one right after the other. So the preemption gives you the multi-processing for the most part. So we're taking I.O., we're putting it in a preemptive kind of concept. We're stopping and we're going to say, okay, you're bound for I.O. You go into that queue over there, and then we run the jobs on a first come, first serve or something from there where those jobs are able to run until they complete. So we only have one job at a time running on anything. We can do that because the I.O. runs simultaneously with the CPU. We're not going to slow the computer down by doing that. If we ran the CPU in a non-preemptive fashion, we would have DOS. We would have one program running, stopping, and then another program running and stopping. So we don't have Windows at that point. Okay, so context switching, short-term, medium-term, long-term scheduling, critical region, mutual exclusion. Think about the assignment on the CPU scheduler. Know how you're going to measure the efficiency of one scheduler over another. What were some of the criteria, as an example? Some of the criteria that I talked about in this class, actually, was on one page, and I pointed the page out, and that was the criteria that was listed for the assignment on CPU scheduling. Throughput, CPU utilization, wait time, average wait time, average turnaround time. Yeah, CPU utilization. I think I said that one. I don't know. Throughput. Did I say throughput? Anyway, those are just some off the top of my head. Because you're probably gonna be asked, how are you gonna compare one against the other, or something of that nature. Hey, we got through page 1. And that was page 1 only has I think it has 7 questions on it. We're 7 questions in. We're good. We're good to go here. Question number 8. Or do we have questions on the concept of CPU scheduling or processes?
How many questions have you?
Good question. Probably only one. Just kidding. No, there's more than one. There's one on the queues, the short-term, medium, long-term. There's one on context switching. There's one on mutual exclusion and critical region. One on interprocess. And one on CPU scheduling on the first page. No, you must have come in late. Everyone's going to beat you up right now. Don't ask that question. I'm sorry? You came in late, yeah. It's obvious. I was saying I gave a student the multiple choice exam because she really wanted to take it earlier. And I said, are you sure you want to do it? Because you're going to be my guinea pig here. And she failed it. Didn't even get half the questions right. then I decided that's not really fair. I can't give you a multiple choice. It's because if multiple choice is too specific. Yes, it's easier to guess at the answers, but you're not going to score as well. Long story short, unless y'all want to fail it, I give you a multiple choice. I was under the assumption you wanted to pass it. So. All right, so question number 8. All right, so in interprocess communication, if we're using a mailbox approach, what problem do we have? This is just trivia question. It's not a question on the exam. We have a situation where we are introducing busy waiting. So know what waiting and busy waiting are as concepts. So as an example, if a process is going to go check a mailbox or check a shared value in terms of even using a mutex actually, from a non-kernel level implementation where we're not sleeping and waking up processes, they're doing something. They're going to go check a value. They all get a turn in a cycle. They go, can I run yet? Okay, let's go see. Nope, I can't run yet. And then they go back to sleep or they wait. And in the meantime, they're not running, but they're busy checking to see if they can run. So busy waiting is the energy as a process you're putting out to see if you can run when you can't run, versus not putting the energy out at all. And then when I was in class, I remember the example because I was thinking about it. I'm like, well, that's a really bad example with the bathroom. If you must use the facilities and the facilities are locked, and you go to the door and you check, like you walk from here all the way over there, oh, it's locked. Oh, it's full. So then you come back and you go over and you check again. Oh, it's full. But you want to use the restroom before you leave the campus or something. Then you're busy waiting. And then I used it with the airplane tries to eliminate busy waiting by putting a semaphore up there. And the semaphore is a little light. It's green or red. If it's a green light, you're not going to be busy waiting. You're just going to look at the green light. Don't even bother. Don't even get up. The getting up and the walking over to check the door is the busy part. You're using CPU time if you're a process and you're doing that. If you're just looking at a light, you're not running anything. You're not doing anything. You're just checking something. So a semaphore is a mutex. Well, it's a way of doing it from a kernel level, so the process isn't busy waiting. You can simulate that using a mutex from a software perspective, then you've introduced busy waiting, because then you have the same scenario. If I have to go get up to go look at a light, and then I look at the light, oh, no, isn't that the same as checking a door? If I look at a light, check a door, then I go back to sleep or I wait, and then I check again, and then I wait. But if an example of a semaphore is the person who's in the restroom, comes out of the restroom, unlocks the door, comes over and taps you on the shoulder and says, hey, it's your turn. Then it's more efficient. You're not busy waiting anymore. You're doing other work. Or you're just sitting there resting. You're waiting, but you're not busy. You're not constantly worried about if there's some person that's come out of the bathroom yet. Instead, the person's going to tell you when they come out. Better. So know so there's waiting, and then there's busy waiting. Processes have to wait. You can't get around that. You can eliminate busy waiting, though, by using semaphores. Operating system support. If you don't use that, you're going to get busy waiting. Naturally occurs. We also have circular wait conditions. That's if you need 2 resources, or actually not, you can have it with 1 resource. Process A is waiting for process B, who's waiting for process C. Process C is waiting for A, who's waiting for B, who's waiting for C. A to B. I can go around in a circle forever on this one. It means that there's no end to this. They're all waiting on each other, and because they're all waiting on each other, somebody has to stop waiting, put the resources down in order for the block to be removed. So I said block. Well, we have deadlock, and we have starvation that also occurs. So deadlock is the indefinite wait, when there's never going to be a break. So if there's going to be a break, if there's a possibility that the system is going to break up and it's just a long wait, it's not a deadlock. So sometimes we sit in traffic and it's not deadlocked, but it takes us an hour to get to point A to point B when normally it only takes 5 minutes. Not deadlock, it's just slow traffic, a lot of waiting. If you're stuck on the freeway and you're not moving at all and you're just stuck there, even if you're moving a little bit. But then a big old announcement comes down. They do this actually when you go to Tahoe in the winter months. They actually just close the roads if it gets too bad. So if you go in a storm and you're driving, just in case someone wants to do this in the wintertime, some of you guys are new, so you might want to check out Tahoe. There's snowboarding, skiing. It snows in the winter. It doesn't snow in California in the winter. Well, it snows in Tahoe. That's Nevada. Anyway, long story short, you get on the road and it's a 4-hour ride. About 2 hours into it, you know if you're going to get there or not in the snow, because there's actually big old cars that go on the side of the road. They used to do this. I don't know if they do this anymore with all the budget cuts. They used to go, roads are blocked, deadlocked, roads are blocked, deadlocked. And they tell you, oh, that means no one's moving right now, we're deadlocked. And then about an hour after that, they say, you're not getting through, go home, turn around, go home. Which means you're deadlocked because you're not going to move, you're not going to get in, you're never getting to Tahoe. You're not getting to Tahoe tonight. Which is what they're trying to tell you. And then you turn around, you go home, and then you try the next day. Because what's going to end up happening, they actually do. They actually block the freeways completely. They shut them down for 8 to 10 hours, 12 hours, let the snow clear. Because they need to bring the equipment in to clear the roads out. You can't ride on the roads while they're doing that. So it is deadlocked. But that's different than if you left earlier in the day, because you want to leave earlier in the day, because you want to get it before it deadlocks. Because before they block it. So a deadlock is a block. You start earlier in the day, you might actually get past the border into Nevada and you might actually get to Tahoe. It's just going to take you 6 to 8 hours where it normally would take you 4 hours. Yeah. But you still get there. You're not deadlocked. We also have starvation. So, starvation occurs when a process just can never run. It's not deadlocked. It just never gets a turn to run. So think about the concept in which you run out of gas. You expelled a bunch of energy to get to Tahoe. You can get to Tahoe, no problem, but you don't have enough gas. They didn't give you enough gas. And you burn through all your gas trying to get there, and you're never going to get to Tahoe. Instead, you're parked on the side of the road while everybody else is going to Tahoe, and you're starving. Because you don't have enough resource, and the resource you don't have enough of is the gas, and you need that gas in order to run. So it's depriving a resource to a process, not allowing a process to use a resource long enough so that the process cannot perform its job. So you starve when you're the last person in the queue, you don't have an aging on the queue set up, and you're not allowed to use the CPU. But you can use the I/O all you want, but you can't use the CPU. You can still run. You're not deadlocked, but you're being starved. And you're never going to run because you're never going to get access to those resources that you need. So it's kind of like humans, actually. Eventually, you're going to die if you don't eat, and you're starving because you're not getting enough resource. So eventually you're going to dwindle down to nothing, and then you're going to pass out and die or something because you're not getting the resources that you need. Same concept in the real world, actually. So processes starve all the time. They never run. They're waiting for what? Because you need something and you're not getting it, usually memory in that case. So starvation, deadlock, busy waiting. Those are concepts of interprocess communication that work for threads and processes and process control blocks. And so the concept, you have 2 questions on deadlock, actually. I see 2 questions on deadlock. One of the deadlock questions is actually a starvation crossover, working with the concept of starvation and deadlock together. So I call it a crossover question. It's on both. Oh, let's see. We actually have 2 questions that are on the short-term, long-term, medium-term scheduler queues. It's two queue questions. I'm looking at the rest of the questions on the second page. And another question out of chapter 1, actually, on this page too. So we have one that deals with operating systems in general as a concept. That's out of chapter 1. I know the different types of operating systems, so you can compare, contrast, or kind of deal with the concepts. I mean, as a generic, question to ask yourself, going into a final exam for an operating systems course, can you actually, if I ask you, well, what's an operating system? Can you answer that question? And then, what services does it provide its users? And what are different types of operating systems? Actually, I'm going to ask you this question then because I'm kind of curious to see what people will respond with. Give me 3 different types of operating systems. Just spit it out. 3 different types of operating systems. Brave people will say something. Micro? Oh, microwave. Microwave, yeah. What's another one? Cell phone, mobile. Oh, so you guys are smart. You guys got it.
Actually, people have gone through your forums, I guess.
Yeah.
I've seen this question in your.
I ask these questions all the time.
I've
Yeah.
seen this also.
Yeah. I say, what are the different types of operating systems? It's funny.
They say like MS Office, Linux, like that.
Ah, so you don't even know the bad answer to the question.
The other places like microwave, telephone, and whatever the machines operates through electronically, it's kind of another operating system.
Yeah.
That's what you expect to answer, right?
Yeah. The wrong answer to the question, and okay, so now my mass communication through YouTube and everything else and my forums have definitely made an impact. People know what an operating system is now. For years, I used to trick people up on this question. And 50%, 60% of the class would always miss it. And no matter what school I was teaching at, no matter where I asked the question, people would say, if I asked the question, if I said, give me 3 types of operating systems, they come back and they say Windows, a Linux, a Mac, a PC, a DOS. And that's for those people who are not understanding it, that's the wrong answer to the question. Those are not operating systems. Those are desktop systems. They're all one brand. They're not one brand. They're different brands, actually. They're different brands of the same type of operating system. It's a desktop personal computer operating system. You could argue and say Unix is a client-server or distributed operating system. So the correct answer to that question is a mobile device operating systems. Yeah, microwave falls in the category of a component, of an electronic component. Actually, your watches have operating systems. Your microwave ovens, your toaster ovens, anything that allows the user to come over to it and press some buttons and use the thing. There's an operating system. Your printers have operating systems on it. So, network routers have operating systems on them. So there's a million. Everything in the world has an operating system. Even the clock on the wall has an operating system on it. So yeah. Anyway, so I'm glad I've made an impact on the world. People know what an operating system is now. It's the funniest thing because I used to ask it on midterms and stuff, and people used to go, well, what is this operating system thing, Hello, All right.
Probably will not be answered. Asking this question again.
Who knows? I like to ask it because I always like to mark it wrong. It's not sadistic. It's just like, when you say, it's like putting candy in front of a baby, and then they're going to take it. When they don't take it, you're like, wow, how come you didn't take it, It's fascinating for me to see. And there's a couple of other questions I always ask, too, because it's fascinating to see what people answer with. That's not so much entertaining anymore. I like, like
situation, how many processes are required minimum?
Oh, yeah, I don't ask that one anymore. But, yeah, I used to ask, there's a multiple choice question. Everyone gets this one wrong. I'll ask you guys, well, you guys know the answer because I've already said this 1,000 times to you guys. But how many processes does it take to create a deadlock? And the answers are 0, 1, 2, or more. Or two or more, I think, is the way that is answered. And then, like 90%, I did this at ITU, actually, last time I taught this class. The multiple choice question that came out of that, everyone said 0. And then the people who didn't say 0 said 1. Nobody said 2 or more. Like 90% of the class failed that question. You can't. How are you going to deadlock with yourself? If there's no processes running, how are you going to deadlock? Anyway. And I actually got that off of a textbook. There was a textbook that had that in there. not this version, but a different book, operating systems book. And in the teacher's note, teacher's edition of it, they have these questions, you know, and it says, ask this question. Like, oh, okay, I'll ask this question. And I'm like, oh, that's funny. All right, so let's continue with the final exam. So we've gotten through CPU schedulers. What came after that? Memory. So naturally, and you have assignment on memory, and the memory that you have an assignment on has little terms in it. Terms are internal and external fragmentation, main memory, logical memory, physical memory, memory management, all those little concepts about memory. The exam goes through memory, I believe, and then I dropped it off. Let me just make sure. Yep. It's just goes through that chapter on memory, and I'm going to finish that up today. Actually, I have a little bit left on that to show you. But examples of the different types of memories. Be familiar with examples of, you know, what's physical memory? Well, it's the chips, it's the boards. And then the MMU turns it into logical memory. And then from logical memory, we can abstract this concept of main memory. Well, it's the operating system's interpretation of the logical memory that comes from the MMU. And we use the main memory, great, but how do we make it twice as big? Or, well, we make it virtual. So it's actually kind of easy to remember if you think virtual doesn't exist. Main memory, there is a mapping. It does actually exist. Physical exists, actually. Physical exists. We have the logical representation of the physical. We have the main concept of the main memory that's based off of the logical memory. So a lot of people use the word main and logical interchangeably because it's really the logical memory representation. Virtual memory is a totally different concept. We take that main and we abstract it out into something that it's not. We make a virtual representation of it to make it, well, why are we going to do that? Make it bigger? Because now we have more of that resource to play around with. When we make it bigger, then we have to use this thing called a backing store. We can use a backing store to keep track of stuff that's actually not in the virtual, and then we can put things into the virtual when we need to run it and use it. So we have this thing called a page table. We have pages and we have frames. So frames are the logical representation of the memory. We take the frames, we stuff them inside of pages. We put it in a page table and allocate pages to process space, and now we have virtual memory. Why do we do that? Why bother paging? Actually, this is a good preview question for you on the exam. Why bother using pages? Why do we even bother with that? Because if we don't, okay, give me 2 seconds, I have to answer this question. No, you can come in. If we don't, then we're dealing with contiguous memory allocation. So paging, page tables, frames, all that stuff is created and virtual memory is created, so we don't have to deal with contiguous memory. We can make memory, we can use memory all over the place and not have to worry about a hole big enough to fit whatever it is we need to run. Okay, on that note, we'll stop momentarily so he can take attendance. So it's now official on Wednesday. The exam start time is 11 a.m. Runs from 11 to 1. So if you want to take both exams on Monday, you can. One's at 11, the other one's at 2. If you want to take one on Monday and one on Wednesday, you can take anything you want at 11 a.m. Well, of those 2 classes. So you can take the operating systems one or the engineering management one at 11 a.m. on Wednesday if you don't want to take them both on Monday. Because I know a lot of you are enrolled in both of those 2 classes. So it's a lot to take for one day, back to back. So, questions about the exam times? Yeah, on Wednesday, it's 11 to 1. 11, 12, 1. Yeah, about 11 to 1. If someone's in here taking the exam and they came in on 11 and they're still taking it, we'll stay longer.
On Monday?
On Monday, it's the normal. So on Monday, it'll go from 11 until everybody finishes, and then from 2 until everybody finishes. Show up at 11 or show up at 2 on Monday. Show up at 11 on Wednesday. If you show up at 2 o'clock on Wednesday, you're not going to be able to take the exam. You have to show up at the start time, and then you take it until everybody finishes. Does that make sense? Because I don't want people coming in and coming out, coming in and coming out while they're taking an exam. So it's the start times you have to make. If you're like 5 minutes late, that's fine. You're just going to cut your time short on the exam. So, most of you are actually much better at showing up on time these days. I think it has something to do with the attendance. I'm not sure. Anyway, let's go back to the exam review. We haven't finished that yet. So, I talked about internal and external fragmentation. And I think I ended with that question about the page tables and why we need that. Well, because in main memory, we're generally talking about contiguous memory allocation. Contiguous memory allocation is one block after another block after another block, putting all the process memory together in blocks that are available that are next door to each other. Not too efficient because we end up allocating and then deallocating and allocating and deallocating. We have these holes that show up in the memory, and the holes cause problems because we have the situation in which we have a process, but it's too big and it can't fit into the little holes. We have enough memory. So external fragmentation is when we have enough memory to load the process, but it won't fit because we don't have enough contiguous memory allocated spaces available. We don't have a hole big enough. Internal fragmentation is when we've taken a big hole and we've put a process into it and we have extra space the process isn't using. It's internal to the process space that's already been allocated for that process, but the process isn't using it, so nobody else can use it either. Fragmentation as a concept is pieces, little fragments or pieces. So those are the fragments. They're either internal or they're external to the process space, causing the fragmentation. All right, so we have contiguous memory allocation in main memory. We have non-contiguous in virtual memory. Virtual memory is non-contiguous memory. We take a bunch of frames that have been created. So we define, a starting address, and then we have an offset, and we say that that's a chunk of memory that we're going to use as a frame. We take the frames and we allocate them to the pages. We take the pages, we allocate them to the process. The page table holds those mappings. So then we have frame tables. We don't really talk about frame tables. That's really done at we can actually do this at a hardware level, or we can do it at a software level. No hardware questions. No hardware implementation questions of page tables, because we can put a page table in hardware. Or no frame, hardware, anything, nothing about hardware, completely software exam. But knowing the differences between logical, physical, main, and virtual are important. When we actually go to run something, I actually asked this multiple choice question, and I probably gave you guys this one as well. But do we need the physical? The question was getting at when to run a process. Something about which one of these is not needed, and everyone checked the physical because they didn't think they needed physical memory for something. It's like you actually need the physical memory. That's the resource. If you don't have the physical memory installed on the computer, nothing's going to run because none of your memory is actually going to run. So it has to translate down into a physical address eventually. We don't use those physical addresses, however, if we're the operating system. We don't use it. We use the main memory addresses or the virtual memory addressing that we have created as an abstraction. Because we have all this stuff that's not going to fit in the physical all at one time. So instead we branch it out into different hierarchies. We put some on the backing store, we put some in the memory, and then we load it up into the physical banks when we want to do it. And until we run it, we don't necessarily need it. So there's no need to have it in the physical bank. So that's the big concept about how memory works. Purpose of the paging and the page tables. Remember this thing called demand paging? That kind of said, well, we don't allocate it unless we need it. It's kind of like garbage collection. We have garbage collection that works with memory as well. We have to. A garbage collector comes around and picks a victim. What's the victim? Probably the least recently used page because we know it's not going to need to be loaded. Because what we want to try and do is minimize the amount of swapping, and swapping is another term for you. We swap to the backing store. We don't swap to swap drives. We have it. It's called a backing store. The swap drive was somebody's really good, ingenious invention about creating more memory. Swap drive is generally formatted like the main memory, and it just gives us more main memory. We swapped the hard drive space to secondary, and we turned it into primary memory, which is where that term comes from. To swap something, however, means to pull it out of memory and put it on a backing store. So when I ask that multiple choice question, everybody misses that one normally because they think, oh, you swapped to a swap drive. No, you swapped to a backing store. Swap drive is a completely different concept. It's the only thing in common is the name of the drive. Pretty much the words swap and swapping are very similar sounding. You know, they're kind of almost the same word, right? But two different concepts. So that's why you don't want to have a multiple choice question like that, because then you're going to naturally go, oh, that looks like the right answer. No. Anyway, backing store is formatted just like the main memory. However, in fact, there's similarities because swap drives are formatted like the same memory as well. But the swapping technique is the matter of pulling it out of the main memory or the virtual memory, putting it into the backing store, and then reloading it again. So swapping is taking something out of memory, taking something and putting it back into memory, going back and forth. When you swap at a high level, you have very low CPU utilization, and you have what's called thrashing. So thrashing occurs as another vocabulary word for you. Your system is thrashing. When the CPU utilization actually goes up, the CPU is actually being utilized 100% of the time, but it's not doing any work. Instead, it's swapping something out of memory, putting something back into memory, swapping something out of memory, putting back something into memory. Why is it doing all that stuff? Because it's trying to get the program into memory so it can run the program, but it can't run the program because the program won't fit. All the swapping efforts are exhausted because eventually that program it can't run because it's never going to all fit in memory all at the same time. We want to avoid thrashing because then we have it's like context switching constantly without running a program. Not such a good efficient use of the CPU. We have to use CPU cycles just like we use CPU cycles in context switching. We use CPU cycles to swap. And what we're swapping is, the memory locations themselves. So we have these things called valid and invalid bits that get held in the page table. Yeah, in fact, I don't even have to go through this lecture now because this is what I was going to tell you today was the stuff I'm telling you now, actually. So today's lecture was finishing that other lecture that we were doing, but I can just summarize it all for you right now. We put a valid bit in the page table to indicate that the page is owned by the currently running process. And that is part of the process's memory. It's invalid when it's been swapped out. So the swapping techniques changes the bits because we need to know if the page belongs. Has it been changed? Does it belong? Did another process use it? Do we recycle that page? So we have this thing called a page fault that occurs. And I talked about page faults last time, and that's where I was going to pick up on the lecture today. But I can just discuss it right now with you. A page fault is when the page isn't loaded in memory. It's when we have an invalid bit. It's not an error. So this is the other multiple choice question about page faults. People think, you write a question, it says, a page fault is a memory error. No, it's not an error at all. It has nothing to do with errors actually on the system. In fact, the lecture I'm talking about, just so you have an idea, is lecture 9B. In lecture 9B, 9A and 9B are where we ended. 9B was today's. And it goes through the concept, actually 9A, the one we did last time, was based on chapter 9 of the text that goes through the memory management stuff, which follows 8. And 8's the main memory, and then we have virtual memory, which was 9. So you want to make sure you read through those chapters. The virtual memory one, this one here, 9B, goes through a bunch of concepts regarding the differences between logical and physical, definitions of binding, compile time, execution. I didn't put anything on the exam, actually, for binding times. There's no binding and there's no allocation questions on the exam. There's actually nothing, because we didn't really get into it, there's nothing on the different memory management schemes either. So I don't even necessarily need to cover, but we did cover a little bit when it came to contiguous. We had the first come, first serve kind of thing. We had the, picking the biggest available space versus the smallest available empty hole for the whole allocation. And then if you go through this lecture, you'll see some of that as well. You'll also see allocation schemes. You don't really need to worry about that either. Or you don't have to know about relocation bits, relocation registers. Nothing about that at all either. But job scheduling at around this particular slide here, which looks like at about 15, looks at the differences with memory and job scale and memory management and job scheduling. Just like CPUs, schedulers work with process concepts and kernel process storage, it also works with memory. There's a relationship between the CPU scheduler and the memory management as well. Because when the kernel does its context switch, finds a process, well then it's got to work with the memory management routine to load that process into memory. When it goes to load the process into the memory location, or to go find it at the memory location that this PCB seems to think it's at, that's when the page fault occurs. It goes over and it looks at it and says, hey, we're going to that process we saved a while ago. Let's reload that instruction that we wanted to run. Oops, not there. That's a page fault. So the page fault says, well, let's go to the backing star. Is it on the backing star? No, not on the backing star. Okay. Yes, it's on the backing star. Then we load it from the backing star, and then we are allowed to restart the instruction and continue our processing. If it's not on the backing star, then we got to go to the disk and load it fresh. Take it out and load it up into memory, and then restart the process. The page fault always requires a restart of the instruction because we can't run the instruction because we don't have the memory. The memory's there. We didn't run out of memory. We still had the piece of memory, but somebody else used it while we were sleeping. And the bit's now invalid. That's a page fault. A page fault just allows us to, it's a trap to the operating system to say, hey, go load something because it's not loaded. It's not an error. It's not a memory error. It's not exception handling. It's nothing like that. Although it sounds like it because it says fault. We created a fault. Now it's an invalid bit. They should really call it page invalid. But it's invalid because but it doesn't belong to the process. So in this memory, we have that contiguous memory allocation. So this is 9B, by the way. So if you need a refresher on the different, this lecture is good because it puts all the pieces together. So then the long-term scheduler for memory and compaction. No questions on compaction or defragging, but you guys probably know that stuff already. There's some information here on pages and page address schemes. No questions on the exam on page address schemes either. So I see the words page fault written on the page. I see the words demand paging written on the exam and a question. So we know we want to know about page faults. We want to know about demand paging. Demand paging is basically using paging, but waiting, delaying the execution. Or not the execution, excuse me, delaying the allocation of the memory until it's actually being used. So how can we do demand paging? Well, we can have dynamically linked libraries and dynamically linked components in object code. Which means, and then the concept of dynamic libraries and things is important because then you know, well, why are we doing any of that stuff? Because we're trying to reduce the amount of memory we actually need. So, long story short, if we have some reasonable code that everybody's using, if it's loaded up into memory, why don't we just call to it? Why do we have to load another copy of it up there? If we're keeping track of it, then we can just call to it. And if that's the case, then, you know, when we need it, we load it. If it's not there, otherwise we look for it. If it is there, we share it. We look at it. So that's where shared objects, dynamically linked libraries, and everything else fits into the memory concept. So nothing on that, actually, which is interesting. I do see a question I have to pull off this exam, actually, because I'm looking at the question. I'm like, it's kind of worrying. I might change it with another one. So, do we know what we didn't cover? Actually, let me mark this exam. Actually, there's 2 questions. Actually, I have to remove. 3 questions I have to remove. So I found out where I'm going to give you your 3 extra points. I can remove those 3 questions. The 3 questions are on secondary storage, but we didn't cover secondary storage. I was looking at this exam because I thought I had an extra week actually. So we're not going to cover secondary storage. So one of these questions is on LinkedIn indexed, Index versus linked allocation of disk space. I can't ask you that question. I never covered that question. And also the other one's on disk scanning, disk reading algorithms, which we didn't cover, and RAID systems, which we didn't cover. So what I'm going to do for you is pull those 3 questions off the exam, and then not replace them with anything. Because remember, in the beginning, everyone's so excited. Oh, I get 5 extra points. Now you get 3 extra points. So I figured out a way of compensating here. So there's only going to be, there's out of 25, there's only 22 questions now. So there's 22 questions, and each one of the questions is worth 1 point. So you can get 20, and then you get 3 extra points. So you're guaranteed 3 points when coming into the exam to take it. You got 3 points, you just got to get the rest of the points. Because we did not cover secondary storage. But that's actually the rest of the that's actually the exam. I've given you all the questions on it. What I was planning on doing, and I don't really need to do it if you guys aren't going to do it on your own, is finish this 9B lecture today. But I can show you what's in here, and I can tell you that 90% of it outside of the paging is not on the exam. So. I tried to cover on the exam what we've covered in the class, and we didn't cover very much. We just basically tapped on a little bit of the memory. I did spend a couple weeks going over the differences between the main memory, the virtual memory, the logical memory, and the physical memory, but I didn't do very much on page tables outside of the concept of a page table. So the concept of the page table is on there. Nested or hierarchical multi-level page tables, no. Be familiar with what a page table is. The concept, I'm sorry? Demand paging is creating and allocating the memory when it's actually being used. So the question was asked what demand paging was, and I answered it. So some of you people who weren't paying attention probably might be interested in knowing. The question, you want to know what demand paging is, actually. And so it's not allocating, it's delaying the allocation until the memory is actually needed. So when we need a page, don't make them ahead of time. If you demand it, then you can actually use the resources more efficiently because you'll have full access. If you pre-allocate all your pages and you create them all for your processes ahead of time, and don't do it on demand, don't delay it, it makes everything run slower because you're spending the time to allocate the memory before the process even runs. Why don't you just wait till the process runs, and then when the process is running on demand, allocate those pages. So there's a lot more explanation of that in the text as well. So, but you don't have to know about multi-level. You don't really need to know about hardware either. The concept of segmentation is also not on the exam. So I guess it doesn't make any sense for me to cover material that's not on the exam. So paging, demand paging. Here's the demand paging, actually right here. Demand paging is in 9B. So there's some good stuff out of 9B that you might be interested in looking at. It's also in the text as well. In fact, this is a page fault diagram, actually, looking at virtual memory demand paging. So, in theory, we want to reduce the number of page faults as possible. If we're doing demand paging, we're going to reduce the number of page faults because we're not going to load everything until it's needed. Which means a page fault is when it's invalid. If it's not valid, then if we have the memory, we're going to use it. So go ahead and use it. If you want to reduce the number of page faults, you're going to implement demand paging. So page faults slow us down. We also have page replacement algorithms. Don't need to worry about that either. Didn't really cover it in this course. So no page replacement algorithms either. So. Any questions about what might be on the exam? Or any questions about concepts of what's on the exam? No questions? I'm sorry?
What is important on 9B?
Oh, I just went through that actually, but everything up to and including demand paging. Actually, the thrashing is in here too. But here's thrashing. For those people who missed the thrashing stuff. In 9b, what's important are the concepts that overlapped with 9, which are the concept of demand paging, the concept of paging, no segmentation. There's no segmentations questions at all on the exam. There's no hardware questions at all on the exam. There's no questions about any particular operating system implementation either. And there's no questions about hierarchical page tables or page replacement algorithms. Nothing on that. So just the relevant pieces that are in here. You can probably skip 9b because there's a little bit of overlap. All the 9b information is given in 9. So you might not find 9b helpful at all unless you have a problem figuring out what is a page fault, what is demand paging. The lecture does spend a lot of time going over demand paging. So. Questions? No? All the assignments are due on August 22nd, which is coming up. It's not this week. It's next week, I think, right? August 22nd is next Thursday. Because on August 23rd, I'll be doing all of the grading. I'm spending the entire day and I'm going to grade everything. So you'll know, hopefully you'll know your results on the night of the 23rd, or if not the 24th. I'm giving a midterm. I have a weekend class, the 24th, 25th. So I have not a midterm, a final is happening that weekend as well. So I may not necessarily guarantee to have everything done on that Friday, but I'm shooting for it. Anything else for today? No, then I'll let you guys out a little bit early. Then we're done for the day. I'm sorry? Yeah, 3 or 4 lines, 5 lines. No notes during the exam, no books, no notes, no internet, no electronic devices, nothing. So when you're preparing, just if you can come up with just a vague idea of all those concepts I gave you, you'll ace the exam, no problem. And there's absolutely no way 2 people are going to have the same answers either. Well, I'll hang around a little bit longer if you guys have more questions. Otherwise, I'm done. And you guys already did your attendance, so you're done too. Yeah? Well, you don't actually have to worry about that for the exam. But in general, mutexes. You guys want to know about mutexes, semaphores, counting mutexes? So we have one type of mutex that's 2. It's a binary. It has 0 or 1, which means a process can run, a process can't run. Whose turn, basically giving us reference to whose turn it is. We have counting semaphores and counting mutexes where we have more than one, 1, 2, 3, 4, 5, usually with multiple processes. And it gives different state indication, which means if it's a 3, we have to wait. We're still waiting for a number. We're waiting for 4. We're waiting for 3. It tells us, and we can increment. So if this process is in, this process is in, and this process is in, 1, 2, 3, we're up to 3, maybe, perhaps. Then the number's 3, and then we wait, because we're waiting for number 4 before number 5 can run. So we can keep track of the order that the processes are running, giving a counting order of previous processes that are running or have completed work, to synchronize the work that's being done so one process doesn't try to do work before the other one does. That's a counting semaphore, or counting mutex. Mutexes and semaphores are pretty much the same thing. One's controlled by the operating system, one's not.
So there's no difference between mutex and semaphore? Because I was just Googling and I saw a lot of different, what's the difference between semaphore and mutex?
What is it? What does the Google tell you?
So the Google was telling me that mutex is when you lock it. For example, if I take
when you lock it, a mutex lock is how they're doing it, yeah.
It's 0 and in semaphore it's just you're giving a signal. For example, if you take a red
well, okay, so it's the same concept of of indirect communication, but the mutexes are really, that's actually correct. The mutexes are associated with locks for the most part, and semaphores are not. You're looking at a shared value. Because the semaphore, because you're looking at a shared value and you're not locking, there's no busy waiting. So the semaphore is implemented by the operating system, by the kernel. It has kernel level support. Mutexes are usually done in both. It can be done, well, kernel level supports mutex, but it can also be done in the user mode. So you can create a mutex, and a mutex in that particular case is usually just an integer variable, and it's a counting variable. But yeah, mutexes do lock, and the locking causes the busy waiting. Semaphores don't normally lock. You don't have to lock. Instead, the process just wakes up and says, "Hey, what is that? Oh, no, okay, go back to sleep." It's kind of like when your alarm goes off, and you say, "Oh well, hey, it's Saturday. Oh, forgot. Oh, turn the alarm off, and you go back to sleep." You're not up every 5 minutes checking the alarm. Instead, you just wake up when you need to, because you woke up for some reason, and then. So it's kind of like it's kind of like very similar to an alarm clock. The semaphore in general should work like an alarm clock. You should only have to wake up when it's your turn to run. You shouldn't have to wake up constantly. But if you're using a shared variable to facilitate that, then you wake up momentarily, you check the variable, then you go back to sleep. So that's a good question. Is there anything else? No, then we're done for today. I'll hang out a little bit longer for those people who want individual help.